Hi, this is Robert Owen. Thanks for returning to see part 5 of my series on the use of the Arduino processor to implement the DCC signaling system to control your train. In part 5, I want to explain a bit more what decoders do and how they work, but in particular, I want to explain the difference between the DCC electrical signals that the Arduino passes to the track of your layout versus the pulse width modulation power signals that the decoder passes to the motor on your train. At the top left hand side here, we have an Arduino controller on the bottom and the motor shield on the top. And the controller, or the Arduino on the bottom, contains the program which I explained earlier and I developed to implement a basic form of DCC. The connection from the motor shield to the track is via these two wires from the connectors here. And on the track is the DCC electrical signal consisting of 0 and 1 pulses, represent digital 0 or digital 1, which is between, say, minus 10 or minus 12 volts to plus 10 or plus 12 volts, depending on how you powered it. These are transmitted along the track. They're picked up by the engine of the train, sent to the decoder, and the decoder interprets the data in the control packet that you've been sent by DCC and constructs a pulse width modulation power output signal to send to the motor to command the motor to increase or decrease its speed, to stop, or to change directions. So what DCC decoder should I buy? It really depends on your train and on what you want the decoder to do. There are different shapes of decoder. So the decoder you need to buy needs to fit into your train. So you need to open your train and look at it before you buy a decoder. Some decoders have the connector pins pointing out the bottom. Other decoders have the pins pointing out horizontally. And another set of decoders again have the pins at the end of a small cable. So you need to look inside your train to see what type of decoder it will accept. Also, the larger HO gauge trains will accept a bigger decoder than a small one because they have more room inside the engine. Also, how much do you want to spend on a decoder? The basic decoders will allow you to control the speed of a train. Maybe the lights can be turned on and off in a train, but that's about it. More expensive controllers will control lights. You can control the whistles of the train. You can get the sound of puffing from steam trains. Lights can be turned on inside and outside of the carriages. There's a lot of other things that a controller can do if it has a functionality. A more sophisticated controller can send data from the train back to the DCC controller, say giving more accurate data on its position. But apart from controlling trains, controllers can also be used to control turnouts or level crossings, or to turn on and off lights in signal boxes. Now, my opinion is that decoders are expensive. They're too expensive to be used to control signals or level crossings. And if you're implementing DCC, you'll be better off using other digital logic to control, say, turnouts, and reserve expensive controllers just for the control of the train. Installing a decoder is easy but fiddly. This here in the center is a small decoder. It plugs into the larger circuit board. As you can see, it's quite easy to insert the decoder. The problem is you've got to take the engine apart. You've got to take the top of the engine. Quite often you have to remove the wheels before plugging it all in and then reassembling it. So it's easy to put in, but it is a fiddly job. Now, a decoder has two sets of circuitry on it. First of all, it needs to find 5 or 10 volts power from somewhere to power itself. Once it's got 5 or 10 volts power to power itself, it then needs to receive DCC signals, packets, decode them, convert them into pulse width modulation signals to control the engine. So let's first look at the way the decoder generates a 10 volt or 5 volt DC signal to power the decoder. The DCC signal on the track is, say, plus or minus 10 volts or plus or minus 12 volts, whatever you've implemented it. It's picked up by the wheels. It goes to the decoder. The decoder has a module on it, a full wave rectifier, and it converts this plus or minus pulse signal to a steady 10 volts. You can see plus 10 volts here, plus 10 volts here. The minus 10 volt pulse here is converted to plus 10 volts here. So once it goes through the full wave rectifier, you're going to get a steady 10 volts power or 5 volts power to control the circuitry or to power the circuitry on the decoder. Next, once we've got power to control the decoder needs to receive the DCC packet signals, extract the control byte, and convert it into a pulse width modulation signal to power the motor. So this again is the same DCC signal. It was transmitted on the tracks. It goes to it's picked up by the wheels, but it's transmitted to a different part of the controller. The controller analyzes the DCC packet, extracts the control byte, decodes it, and converts it into pulse width modulation power for the motor. So those are the two parts, or the two separate functions of the decoder. To control speed, as I explained in a previous video, a packet of data in its very simplest form consists of 4 bytes. A preamble to indicate to the decoder that a byte is about to be received. The address of the engine. If there's more than one train on the tracks, each engine needs a separate address. The default for all decoders is 311. So if you've got more than one train running on a track, you need to change the address of at least one of the decoders. The third byte is the command, and the command could say run engine at this speed, or change directions, or stop, or switch these signals, switch these points. And the fourth byte is error check, to make sure that the packet was received correctly. If the packet wasn't received correctly, the decoder would discard the entire packet and wait a few milliseconds for the packet to be received again, because the packets aren't just sent once, they're repeated over and over until a new command comes. DCC versus pulse width modulation. This is a DCC electrical signal, as we'll see on the track. It's a series of plus or minus 12 volts or 10 volts digital pulses to represent ones or zeros. This is on the track. It's picked up by the wheels of the train, sent to the decoder, and the decoder looks at the command and generates the appropriate pulse width modulation power signal for the motor. If the pulse width modulation signal is between 0 and 10 volts, the train goes forward. if the pulse width modulation signal generated by the decoder is between 0 and minus 10 volts, the train goes into reverse. And if there's no pulse width modulation power, the train stops. So quite straightforward. Plus voltage, the train goes forward. Minus voltage, the train goes into reverse. What about the speed of the train? How does pulse width modulation control speed? If the pulse width modulation signal from the decoder to the motor is a constant 10 volts, the train goes ahead at full speed. If the pulse width modulation signal is 80% of the time there's power and 20% of the time it transmits no power, so the average voltage being transmitted is only 80%, the train will move forward at 80% of its full speed. If the pulse width modulation pulse is only on for 20% of the time and off for 80% of the time, the average voltage is only 20% of the full voltage, so the train will move ahead at 20% of its full speed, quite slowly. This is for pulses between 0 and 10 volts. If the voltage is between 0 and minus 10 volts, as I said previously, the train will go in reverse. For a pulse that's minus 10 volts for 20% of the time and no voltage for 80% of the time, the train will go in reverse at 20% of its full speed. So how is this implemented on the motor shield? The schematic on the right shows the connectors on the Arduino or on the motor shield. I've left out the integrated circuits because they're not necessary. So these are the connectors on the motor shield on top. This is another view of the motor shield. In this one, I've removed the connectors in the middle because they're not being used. We have two output channels, channel A and channel B. Channel A is the plus and minus signals, plus and minus voltage, to transmit a train on one track. And channel B, or circuit B, controls a train and sends signals to another train on a completely electrically separate track. Usually what happens is channel A controls the main line and the running of the train. Channel B sends signals to a small dedicated part of the track that's used to alter the address of the decoder or to change other parameters within the decoder. But in this series, I'm only going to look at channel A, so I'm going to remove channel B commands from the slides for simplicity. But what I say for A applies for B. So using the motor shield for DCC, it's important here because in a later slide I show using the motor shield for pulse width modulation, which we don't do in DCC. The decoder does it, but I'll explain it for interest. So for DCC, pin D3, PWM is called, is always set at plus 5 volts, digital high. So the output from D3 is always at D3, it never changes. Brake A, pin D9, is used in pulse width modulation as an emergency brake. We could implement it in DCC, but we don't. So pin D9 is just left alone. It's automatically activated or deactivated, so it doesn't break the train, so we ignore pin D9. Pin D12, DRIA, is a direction. And what we use this for is, using pin D12, we set up the DCC pulses. If pin D12 is 0, as here, out of connector A, you get minus 10 volts. If pin D12 is plus 5 volts, out of connector A, we get plus 10 volts. So by modulating this between 0 and 5 volts from the Arduino, the output from channel A changes between minus 10 volts and plus 10 volts, which is a specification for DCC signal to go onto the track of your layout. Okay, so this is how the Arduino sets up the DCC signal. So this is how it's set up for DCC. If now we want to set it up for pulse width modulation, you're not going to do this with DCC, but say you were implementing a robot and you wanted to directly provide pulse width modulation to the power, so there's no decoder involved. The output from these signals is a bit different. Now at pin D12, if the motor is moving forward, it's constantly at 5 volts, it doesn't change. Okay. Pin D3 now modulates, forms digital pulses with a duration on and off, depends what you want the pulse width modulation signal to be. And by feeding this data into the motor shield, the output from channel A is between 0 and 10 volts, the pulse width modulation power that we want to control the motor on the robot. So this plus 5 volts from pin D12 is always on when we want the motor to go forward. Okay, again for pulse width modulation. If you want the motor on the robot to reverse directions, we change the power on pin D12 to 0, logical low. And we still have the same pulse size, but the output power from channel A will go from plus 10 volts here, and where digital 0 is here, it'll go to minus 10 volts, reversing the speed of the motor. Now, in reality, you're not going to suddenly switch the motor speed from forward to backwards. There will be a gap here where the motor is stopped and then go forward. So that's the difference in the way the motor shield implements pulse width modulation compared to the way it implements DCC. Okay, so that's a bit more background on the motor board, okay, on the motor shield and the difference between DCC and pulse width modulation. At the end of video 6. My next video, also the end of video 5, and my next video, part 6, I'll explain how to use the LN298N motor board as an external controller for DCC instead of the attached motor shield, which is attached directly to the Arduino. So LN298 is a different functionality, it's a different way of connecting it, and it has different software and slightly different software to enable it to run DCC trains.